Up to this point, we've been studying the motion of objects by describing their velocity, position, and acceleration. You might be wondering, though, how does an object get an acceleration? What's changing the velocity? Why does it have the position that it does? These were questions that Isaac Newton thought about 400 years ago. As the story goes, Newton was sitting underneath a tree studying, and he saw an apple fall. Sometimes the story says the apple actually fell on him. He thought maybe there's a force, as he described it, that's causing this motion to occur. And by thinking about the motion of objects in this way, Newton formulated what are called Newton's laws. The first of Newton's laws is the statement that an object in uniform motion will remain in uniform motion unless acted upon by a net external force. So this is to say, if something is moving with some constant velocity, if no force acts on it, it's going to continue on forever without any change in velocity. The special case of this law is to say that an object at rest will remain at rest unless acted upon by an external force. Newton's second law tells us that the sum of the external vector forces acting on an object is equal to its mass times its vector acceleration. Now it's a very specific way to describe this, but there's a reason for it. And we see the reason when we look at the equation. And the equation puts this very succinctly. This just says the sum of the vector forces is equal to the mass times the vector acceleration. Now, the reason why you cast it in this way, as opposed to just saying the force is equal to mass times acceleration, is because you want to consider the fact that there can be multiple forces acting on an object, and it doesn't necessarily move in one direction. So you can also cast Newton's second law in component form to say that the sum of the forces in the x direction is equal to the mass times the acceleration in the x direction, and the sum of the forces in the y direction is going to be equal to the mass times the acceleration in the y direction. Now, looking at Newton's second law, we actually already have some intuitive understanding of it if we consider our ability to push something. So, for instance, if you have a younger brother or sister, you might have pushed them on a swing before. You provide some push, and that causes them to accelerate on the swing. But if you provide that same push to a train car, what you find is that you're not able to move the train car very easily. And this is because the train car has a much larger mass than your younger brother or sister. Okay. Newton's third law is the law that says for every action there's an equal and opposite reaction. Another way to put this is it pertains to the force that acts between two objects. And so that's to say, if there's these two objects, the force that object 1 acts on object 2, which is what this statement right here is saying. So the force that object 1 acts on object 2 is going to be equal to the negative of the force that object 2 acts on object 1. And so another way that you can think about this is, I'm standing on the ground right now, and I'm exerting a force on the ground. There's an equal and opposite force that it has the same magnitude, and it's pointing in the opposite direction as the force that I'm applying to the ground. So what are some examples of force? The most obvious example of force is the force of gravity. This just says that the force of gravity on any object close to the surface of the Earth is going to be equal to the mass of the object times the acceleration due to gravity. In SI, the acceleration due to gravity has a value of 9.81 meters per second squared. Another common force is what's called the normal force. So when you think about normal in the context of mathematics, normal means perpendicular. And that's exactly what a normal force is. It's a force that's perpendicular to a surface. So if you have some object sitting in my hand right here, and like a block, the normal force would be the contact force between my hand and the block such that it's perpendicular to my hand. Another common force we'll find is tension. So tension, an example of tension is if I have a block and I'm hanging it from a string. The string is providing a tension force that holds the block up. Another force that we'll see fairly common is the spring force. So we're all familiar with springs, but we have a very specific way to describe the spring force. And that's to say the spring force is going to be equal to negative times the spring constant times the amount that you displace it. So the more you compress a spring, the more force it exerts back. Two more common forces are the force of friction, and there are two ways that you can look at the force of friction. One is the static force of friction. That's a force of friction that you experience if an object's not yet moving. And so the important part to the force of friction is it's it's partially dependent on the normal force that's exerted on an object. It's also related to what's called the coefficient of friction. This is the mu sub s that we have in this equation. We note that this is a little bit different than the kinetic force of friction, which says that the force of kinetic friction is going to be equal to mu sub F times n. So the real difference between the static force of friction and the kinetic force of friction is this inequality that we have here that says that the static force of friction is less than or equal to the coefficient of static friction times the normal force, whereas the force of kinetic friction is equal to the coefficient of kinetic friction times the normal force. So this is something that you have to bear in mind and be careful of while you're solving problems. Okay, so now what we'd like to do is we'd like to put together a roadmap or a general way that we can solve just about any problem with Newton's laws. So the first thing that you want to do when you're solving a problem with Newton's laws is to draw a big diagram of the situation. So this could have anything that you'd really like in it. You can add trees, you can add flowers, but it's really meant to help you visualize what's happening with the motion of the object. Once we have the big diagram, we make what's called a free body diagram. So this takes all of the objects that we're interested in finding the forces on and isolates them. So it puts them by themselves. And in doing that, what we want to do is we want to label all forces acting on the object separately using a vector arrow to represent the direction that force is acting on the object. Then we want to draw a coordinate system. Typically, it's an XY coordinate system such that the positive direction for either one of the two coordinates is going to be the direction that the object is going to accelerate in, or if it's stationary, the direction that it would tend to accelerate in. Step 4 of our problem-solving strategy is to write down Newton's second law. That is, the sum of the vector forces is equal to the mass times the vector acceleration. So when you write Newton's second law in this way, you also want to break it into its x and y components, which was really the reason why we drew the coordinate system, because we want to sum the forces in both the x direction and the y direction. The next thing that we can do is we can add in any relevant information to the problem. So for instance, if we had a problem with friction and we had just defined it as the force of friction with some F, we could say that now we know the force of friction is the coefficient of friction times the normal force. The last thing you want to do is make a plan using the equations and the knowns identified in step 4 and 5. I hope this video helps you understand how to use Newton's laws and what Newton's laws really mean. In the next 2 videos, Professor Shepard will be demonstrating the use of the problem-solving strategy outlined in this video. Thanks for watching.